Okay, so we're going to look at this example where we are supposed to integrate this function. We know it's going to be a function of two variables because we have a double integral, even though we only see one there, function of two variables over a region R. It describes here what R is, and so we're going to set that integral up and think about how best to evaluate that. So the very first thing that you need to make sure you do is draw the picture. I always have a lot of students who try to set these up without drawing the picture and then often end up with it set up incorrectly, and then everything else after that is going to be incorrect. So you want to read this carefully. We know that R is going to be in the xy plane here in order to have a double integral. Region in the first quadrant. Okay, so that will be important to make sure that we're focusing on the first quadrant, bounded by x squared plus y squared equals 4. So in the xy plane, x squared plus y squared equals 4 is a circle of radius 2 centered at the origin. If we were in R3, we might call that a circular cylinder, but here we're in the xy plane. Y equals x, that's line through the origin with slope 1, and the x-axis. So here's our x-axis. So it's important that you're clear about what exactly the region is that we're integrating over. So I've just drawn all of the curves here that it described. And these curves cut this region into several separate pieces. So we need to be clear about which piece it is we want. So we're in the first quadrant, and the region needs to actually be bounded by these curves. So those curves need to be edges of the region. So there are two regions here in the first quadrant, but only one of those has all three of these four edges. And the key on this particular one is paying attention to the fact that the x-axis is a boundary. And if you are thinking about this region up here, you're not paying attention to that. You're thinking about the y-axis as a boundary. So the x-axis is one of the boundaries, and then the line and the circle. So we're talking about this region right here. Okay, so then we need to think about setting up our double integral on that region. So we might think about setting this up in xy coordinates. Because we have a circular region centered at the origin, we also might think about using polar coordinates. I'm going to go ahead and set this integral up both ways, but then we're going to talk about how one of those approaches is easier than the other to evaluate. So let's start with xy coordinates first, since that's where we started doing double integrals. So when I think about setting this up in xy coordinates, rectangular coordinates, I want to look at the region and think about whether the region is x simple, y simple, neither, or both. So we're going to think about going through the region in the direction of increasing x or in the direction of increasing y. And if you look carefully at this region, you should see that this region is x simple, but it is not y simple. When I go through the region in the direction of increasing x, I'm always entering at the line y equals x, and I'm leaving through the circle. But when I go through the region in the direction of increasing y, sometimes I'm entering through the x-axis and leaving through the line, and then over here, we would be entering through the x-axis and leaving through the circle. So if I set this one up in rectangular coordinates, we would notice that this region is x simple, but not y simple. So I'm going to set this integral up in two different ways, in xy coordinates, or rectangular coordinates. And if we do that, since the region is x simple, but not y simple, we would do dx on the inner integral. If we did dy on the inner integral, we would have to split it into two separate integrals. The other thing to pay attention to when you set up your integration is the function, whether it's easier to integrate with respect to x or y. This function is maybe slightly easier to integrate with respect to one variable than the other, but neither one is very hard. So because of the region, if we were going to do this in xy coordinates, we would set this up with dx on the inner integral. And then our limits of integration, we would need to think about our lower limit of integration would be where we enter. So that's the line. When I go through there in the direction of increasing x, the line, x equals y. You don't have to write the x equals, you could just write y. And then I leave through the right half of this circle. So I need to solve the equation of this circle for x. So when I do that, I'll subtract y squared and square root both sides. So I get this. I do need to think a little bit about which half of the circle is which. Where x is the positive square root, that would be where the x values are positive. So that would be the right half of that circle. X equals the positive square root of 4 minus y squared. And x equals the negative square root of 4 minus y squared would be where the x's are negative, so on the left half of that circle. All right, so the part that we need here, though, is the right half. So x equals the positive square root of 4 minus y squared. All right, so then we would think about, after I've set up the dx integral on the inner integral, going ahead and setting up the y dy integral and limits of integration for y on the outside here. So once you've set that integral up in the x direction, you can collapse that thing back in the x direction. And what you want to look at then is what's left in that remaining variable. So you would think about the y values that are there. And on a problem like this, a lot of times I'll have students say that the y goes from 0 to 2, which would be the whole circle. But if you notice the region that we're integrating over, the y does not go all the way up to 2. It's this point right here. So we're going to have to figure out the y coordinate of that point. But y would go from 0 to whatever the y coordinate of this point is. OK, so in order to figure out the y coordinate of that point, I'm just going to kind of talk through this and not write out a whole bunch of work just to save some space here. But you're essentially solving a system of equations. So you've got the equation y equals x, and either this one or this one's a little bit easier to work with algebraically. You're solving that as a system of equations. You need the value for y. The x and y will be the same. So you can use substitution. Substitute x for y or y for x. You would have y squared plus y squared equals 4, or 2y squared equals 4. When you divide through by 2, you'll have y squared equals 2. Y equals plus or minus the square root of 2. So on this point, we'll get a y coordinate of positive square root of 2. The other intersection point where we have a negative square root of 2 would be over here. That would be the y coordinate. The x coordinate is the same. You also can think about this as a 45, 45, 90 right triangle and figure that out using some trig there. So, all right, so the y coordinate, though, is what I need for this. And I forgot my x squared on my function, so fix that. OK, so there's the integral set up in xy coordinates. We also maybe want to think about setting this integral up in polar coordinates, because the circle centered at the origin, that's a region that's very simple in polar coordinates. So let's go ahead and set this one up in polar coordinates. And then we'll also think about, if I were going to actually evaluate this, which way would be easier. OK, so if I'm going to do this integral in polar coordinates, I'm going to go ahead and kind of set up a structure here. I need to make sure my function is converted to polar coordinates. So you'll remember from when we used polar coordinates earlier this year, or in some other videos that we looked at here, that x is our cosine theta, y is our sine theta. This is all from trig. X squared plus y squared equals r squared. Those are some of the conversion formulas that you're going to want to be able to use. So x equals r cosine theta is what I'm going to use here. So in place of the x here, I'll have r cosine theta, the quantity squared. So all of this is from pre-calculus or trig. The other important thing for double integrals in polar coordinates is the conversion for dA. So we talked about that in the last video, where we looked at kind of the development of how to think about double integrals in polar coordinates. And for xy coordinates, your dA basically turns into dx dy or dy dx. But remember, for polar coordinates, there's an extra factor of r that is easy to forget. A lot of times I see students forget that. If you have made a mistake on a problem that has polar coordinates and double integration, that's the first thing I would look for. So we talked about where that r comes from in the last video, looking at the geometry of the area of a polar rectangle region is where the r comes from. When you're actually calculating these integrals though, you don't necessarily need to think through where it comes from, but you definitely need to remember to put it in here. Otherwise your answer is going to turn out incorrect. Okay, so my r cosine theta, the quantity squared, is my x squared. For my dA, I'm going to have r times either dr d theta or d theta dr, depending on which way I decide to do the integration. All right, so in deciding which way to do this integration, let's look at this region that we started with here and think about going through that region in the direction of increasing r and in the direction of increasing theta. All right, so if I look at my original region here and I think about going through this region in the direction of increasing r, we'll start at r equals 0. That's at the origin. Remember, you don't really need to use negative r values for polar coordinates. You can if it's convenient, but you don't need to. So I'll start at r equals 0, which is the origin, and then I want to think about going outward from the origin. So when I draw arrows through the region in the direction of increasing r, we are going out from the origin. So we start at r equals 0, and we're always going to be leaving through the edge of this circle. And you can do some conversions. We did some conversions in that review stuff at the very beginning of the semester, where you converted from xy equations to polar coordinates. So you can go through some of that. Or if you really remember what polar coordinate stands for, the r stands for radius. And since this is a circle of radius 2, this equation of this circle in polar coordinates is just r equals 2 in polar coordinates. So our r values, let's go over here, r will go from r equals 0 to r equals 2. And then theta, we want to think about sweeping through that region in the direction of increasing theta. So we're going to start, the direction of increasing theta would be counterclockwise around that circle. So I'm going to start at theta equals 0. And as I sweep through that region in the direction of increasing theta, if you think about polar graph paper, we looked at some of that in that last video also, just those grid lines on polar graph paper along different radii and going around in the direction of increasing theta. So theta equals 0 would be here, and then we're leaving through this line here. You can use some basic geometry to think about that. That's a 45-degree rotation. Of course, if we're doing calculus with polar coordinates, we need to be thinking in terms of radians. So d theta and theta will go from 0 to pi over 4, 45 degrees, pi over 4 radians. Okay, so neither of these integrals is too difficult to actually evaluate the first integration. If I integrate this with respect to x, I would get 1/3 x cubed, and I would substitute my limits of integration. If I integrate this one with respect to r, we've got to do a little simplifying first, but it's also pretty easy to integrate with respect to r first. The second integration, however, is much more difficult on this rectangular coordinate one than it is on the polar coordinate one. The second integration on the rectangular coordinate one, you will have something cubed, and then inside of that you'll have this square root of 4 minus y squared inside of something cubed. That requires a trig substitution to do that integration, and it's not necessarily an easy trig substitution. This problem is much easier in polar coordinates. Generally, if you have a region like this is essentially a polar rectangle. Doesn't look like a rectangle, but it's all constants in the r and theta direction. Notice that after I do that first integration, I'm just going to plug in constants. And so I end up with a much simpler function to deal with on that second integration. So this problem is much easier in polar coordinates. And in general, if you have a region like this, I would consider starting in polar coordinates. If the integration looks like it's going to be tough, then you might consider rectangular. But if you're not told to set the problem up both ways, or not told what coordinate system to use, this is one where polar coordinates is much better. That's something that you want to get better at as you practice these problems, is not only doing what it says in the problem, but thinking about whether you should do it that way if you're given a choice of methods to use. All right, so let's go ahead and talk through some of the integration steps here. I'm not going to write out everything just to save some space, but we'll talk through some of the key steps and get this integrated. The first important thing to do is to remember to simplify this. I'm going to integrate with respect to r, and I have some r's here that I need to deal with. I also have this r here. this r, that's part of my differential for my dA, it does end up being part of what you integrate. So you want to simplify all that before you actually integrate with respect to r. So I'm going to rewrite it, 0 to pi over 4 for theta, 0 to 2 for r, and here I'll have r cubed cosine squared theta, dr d theta. Okay, and then I'll just go up over here and finish that integration. Okay, so when I integrate with respect to r, my integration's pretty easy. Notice that I'm writing my outer integral with integral signs. These should not disappear and then reappear later in your work. That's incorrect work. You're far enough along in math that you should be able to write math correctly. I'm going to integrate with respect to r, so I will have 1/4 r to the 4th, and this cosine squared theta is being treated like a constant in that first integration. Will come along. And then I'm going to plug in my limits of integration from r equals 0 to 2. You can write r equals 0 to 2, or you can just write 0 to 2, but those values need to go in for r. Notice that I have my differential here and my integration symbol for theta, even though I haven't done anything with it yet. It's waiting for me to be ready to do that. All right, we'll plug in the limits of integration here. So we'll put in the 2 first for r. 2 to the 4th over 4 is 16 over 4, or 4. And then when I put in the 0, that will go away. So it won't go away. It'll be 0. So we'll have 4 cosine squared theta after that first integration. Okay, to finish this is why we did some review of integration in polar coordinates, or integration of trig functions, actually at the very beginning of the semester, because when you do double integrals, or later in this chapter triple integrals in polar coordinates, you end up with a lot of powers of sines and cosines. So being able to do all that from what we reviewed that first week is going to help you out here. So this is one you should remember when you integrate even powers of sines and cosines. You need to use that double angle identity. So 1/2 times 1 plus cosine 2 theta. You did that in calculus 2, and we reviewed it early this year. All right, and then simplify and do the integration here. So remember that this 2, I can either pull that out front, or I can go ahead and distribute it through as I do that, but I'm integrating here with respect to theta. So I'm going to leave my 2 factored out. That integral of 1 with respect to theta is theta. And then technically here there's a little u substitution, u equals 2 theta. At this point, probably you should be able to do the integration without necessarily needing to write out the u substitution, understanding that when u equals 2 theta, your du is 2 d theta. You're going to end up with an extra factor of 1/2 to deal with that 2 on the d theta that you have here. So 1/2, and then the integral of cosine is sine. Again, I did not write that out to save some space, but if you need to write out that u substitution in order to do the integration correctly, then do it. It's better to write it out than to mess up the problem because you messed up the u substitution. All right, and then I'm going to go ahead and substitute in my values here and finish the problem. So I have 2 times pi over 4 plus 1/2 times sine of 2 times pi over 2 will be sine, 2 times pi over 4 will be pi over 2, minus, and then all of this with 0 plugged in, so I'll have 0, and then plus 1/2 sine of 0, which is also 0. Sine of 0 is 0, so this whole last part here ends up being 0. Sine of pi over 2 is 1, so I'll have 2 times pi over 4 plus 1/2, or if I want to distribute this 2 back through, I get pi over 2 plus 1. All right, so we want to talk a little bit about what that number means. Remember that a double integral, any definite integral really, but this double integral is a sum of function values for this function at all of the points on this region. When we looked at building those models for Riemann sums and thinking about what those mean, thinking back to that, what you're actually calculating. So this number is the sum of the output values of this function on this region. It's not the area of this region. It is the sum of, if I think about f of xy equals x squared, and I pick points in here, and I plug those points into the function, and I get function outputs, and I add them up over the whole region, times the size of my little rectangles, my partition that we built out of Legos. That's what this number represents. So I'm going to try to emphasize that every time we do a double integral, that we're connecting back to the meaning of it. You should do that too, because you should be able to look at this function and say that actually no matter what the picture of the region looks like, this function never has negative outputs. And so if I got a negative answer here at the end, I would know that I have to have a mistake, because this function, I cannot add up function outputs of this function over any region and get a negative answer. This function only has outputs that are 0 or bigger. So I should expect an answer that's positive here. All right, we'll look at some more examples of double integrals in polar coordinates, and also talking about how do you know that it would be better to do the problem in polar coordinates than to leave it in rectangular coordinates.